Hello friends, I am Chandan. Today's topic is application of steady flow energy equation for open system. Now we know that steady flow energy equation is that H1 plus C1 square by 2 plus GZ1 plus Q, that is equal to H2 plus C2 square by 2 plus GZ2 plus W. So this is the W of control volume. So this is the steady flow energy equation for open system. This is the steady flow energy equation for open system. So this is the steady flow energy equation. Now consider the example of steady flow open system is that is turbine, compressor, nozzle, diffuser, boiler, condenser, throttling process. These are the example of steady flow energy equation for open system. So now I apply the steady flow energy equation for turbine. So consider that first there is turbine. When you consider on turbine, there is some assumption is there. Assumption. You should remember some assumption for turbine. What is that assumption? This must be steady flow. Steady flow. Second assumption is that is perfectly insulated. Third is that change in kinetic energy and potential energy are neglected. So change in kinetic energy and potential energy are neglected. Okay. So what is the turbine symbol? Remember that there is a symbol is there. So turbine symbol is this. The inlet, this is the inlet here. This is the symbol of turbine. So here this is the inlet 1 and this is the outlet 2 and this is the turbine T and work done by the turbine, that is WT. Okay. Now apply steady flow energy equation for this case. First write on the steady flow energy equation first. So H1 plus C1 square by 2 plus GZ1 plus Q, that is equal to H2 plus C2 square by 2 plus GZ2 plus W of turbine. Okay. Now steady flow means you have to apply this equation H1 plus C1 square by 2 plus GZ1 plus Q, that is equal to H2 plus C2 square by 2 plus GZ2 plus W. Next there is a perfectly insulated, that means there is no heat transfer, so that is why Q is equal to 0. Next, the third assumption is that change in kinetic energy and potential energy are neglected. So what is kinetic energy? This is the kinetic energy, and so this is the kinetic energy, and this is the potential GZ1, this is the potential energy, and the GZ2, that is the potential energy. So these are neglected, so that is why this is going to be 0. This is the kinetic energy, potential kinetic energy is going to be 0, and potential energy, this is also going to be 0. Here also going to be 0. So from here you can say that H1, that is equal to H2 plus W of turbine. So from here W of turbine, that is equal to H1 minus H2. Okay. So this is the work done of turbine. So here enthalpy H1, specific enthalpy H1 is greater than H2. That's why this value will be positive. This value will be WT turbine work, that will be positive. That means work done by the system. Positive means work done by the system. Okay. Now second component, second open system, that is compressor. For compressor there is some assumption is there, three assumption is there. Three assumption is there. What is this assumption? First, steady flow. Second, perfectly insulated, same as turbine, perfectly insulated. Third is that change in kinetic energy and potential energy are neglected. So write steady flow. Steady flow means you have to write the steady flow energy equation. So H1. So remember that what is the symbol of compressor? So the symbol of compressor will be H, this. So compressor inlet, this is the this is the compressor inlet, this is compressor, and this is the compressor outlet. So this is 2 and this is 1. Okay. Now apply steady flow energy equation. So H1 plus C1 square by 2 plus GZ1 plus Q, that is to H2 plus C2 square by 2 plus GZ2 plus W of compressor. Okay, now steady flow, that means this equation, and that is perfectly insulated, that means Q is equal to 0 and kinetic energy and potential energy are neglected. So that is why this is 0, this is 0, this is 0, and this is 0. From here you can see that H1 that is equal to H2 plus W of compressor. From here W of compressor that is equal to H1 minus H2. But here H1 is less than H2. So that's why this compressor work will be negative. That means work done on the system. Work done on the system. Okay. So this is the compressor work. This is the formula WC, that is equal to H1 minus H2. Okay. Now consider that nozzle. Third open system device, steady flow open system device, that is nozzle. So this is nozzle. For nozzle there is some assumption is there. There is 4 assumption is there. First, that is steady flow. Second, perfectly insulated. Third, there is no work transfer. And fourth is that the height will be same. So initial height, that is the final height. So Z is the height will be same. So now apply steady flow energy equation, because this is the steady flow nozzle. There is steady flow is there. Steady flow means there is no accumulation of mass or energy inside the control volume. Okay. So apply steady flow energy equation. So H1 so suppose nozzle is like this, focus on that. Suppose this is our nozzle and perfectly insulated means there is no heat transfer from this surface, and this is the inlet and this is the outlet. This is the inlet here, and here the velocity at outlet must be greater than velocity of inlet. Okay, now apply steady flow energy equation, that is H1 plus C1 square by 2 plus G Z1 plus Q, that is equal to H2 plus C2 square by 2 plus G Z2 plus W of nozzle. Now the steady flow, that means H1, this formula is here. Now perfectly insulated, that means Q will be 0. No work transfer, that is W equal to 0, W in nozzle work, and Z1 equal to Z2, that's why GZ1 and GZ2 cancel out. So that is why the formula will be H1 plus C1 square by 2, that is equal to H2 plus C2 square by 2. Okay, now here the velocity C2 is very greater than C1, so exit velocity is greater than inlet velocity. So that is why C1 square by 2 is neglected. So from here you can say that H1, that is equal to H2 plus C2 square by 2. So from here C2 is equal to, so from here C2 square by 2, that is equal to H1 minus H2, and from here C2 is equal to under root 2 into H1 minus H2. So this is the equation. Remember this equation, that is C2 equal to under root of 2 into H1 minus H2, and if it is ideal gas, then C2 will be, that is equal to under root of H equal to, we know that H equal to Cp into T, so Cp into T1 minus T2. So this is the value of C2. In this way you can calculate the exit velocity of the nozzle. Okay, now there is a third device, that is diffuser. That is fourth device, that is fourth opening system, that is diffuser. So their assumption is there. First assumption is that is steady flow. Second assumption is that is perfectly insulated, same as nozzle, perfectly insulated. Third is that there is no work transfer. Fourth is that the initial height, that is equal to final height, inlet height, that is exit height, same. So if you see the diffuser, the inlet is small and the outlet is large, and this is insulated means there is no heat transfer from this surface, and this is the inlet and this is the outlet, and here inlet velocity is greater than exit velocity, because here the area is less and here the area is more. So less area, that means large velocity, and large area, that means less velocity. Okay, now apply steady flow energy equation, that is H1 plus C1 square by 2 plus G Z1 plus Q, that is equal to H2 plus C2 square by 2 plus G Z2 plus W of diffuser. Okay, now perfectly insulated, that means Q equal to 0. No work transfer, that is W, cancel out. And there is Z1 equal to Z2, so that is GZ1 equal to GZ2, cancel out. So from this you can say that H1 plus C1 square by 2, that is to H2 plus C2 square by 2. Here C1 is greater than C2, so that's why this is neglected. So you can say that H1 plus C1 square by 2, that is equal to H2. So from here C1 square by 2, that is equal to H2 minus H1. From here C1 equal to under root 2 into H2 minus H1. Okay, so this is how, in this way you have to calculate the diffuser inlet velocity, 2 into under root H2 minus H1. Important. Okay, now there is a boiler. Okay, boiler. So fifth device is, that is boiler. There is assumption is there, 3 assumption is there. First assumption, that is steady flow. Second assumption is that change in kinetic energy and potential energy are neglected. So change in kinetic energy and potential energy are neglected. Third is that no work transfer. Okay, so first write the steady flow energy equation, that is H1 plus C1 square by 2, H1 plus C1 square by 2 plus G Z1 plus Q H2 plus C2 square by 2 plus G Z2 plus W of boiler. Now change in kinetic energy and potential energy are neglected. So that's why this is neglected, this is neglected, this is neglected, this is neglected. So, and there is no work transfer, that means W is neglected. So from here you can say that H1 plus Q, that is equal to H2. From here you can calculate the Q, that is equal to H2 minus H1. Okay, so this is the formula of Q. So here H2 is greater than H1, so that's why this value is positive. This positive means heat supplied to system, that is heat supplied to system. Okay, now sixth component is that condenser. So apply assumption, there is some assumption is there. First assumption is that is steady flow. For all component there should be steady flow. Second assumption, that is change in, same as a boiler, same as assumption of boiler, change in kinetic energy and potential energy are neglected. Third is that is no work transfer. So apply steady flow energy equation, H1 plus C1 square by 2 plus GZ1 plus Q is to H2 plus C2 square by 2 plus GZ2 plus W of condenser. Now steady flow, this application equation is applied. Kinetic energy and potential energy is neglected, so this is neglected, and no work transfer, that means this is also neglected. So from here you can see that H1 plus Q that is to H2. From here you can see that Q is equal to H2 minus H1, but here H1 is greater than H2. H1 is greater than H2. That is why this value is negative. This Q value is negative. That means heat rejected by the system. That means heat rejected by system. Okay. Now last component, that is throttling process. Throttling process. So seventh component, that is throttling process. Throttling process. For throttling process, what is the example of throttling process? That is flow in a capillary tube, flow through a porous plug, partially opened valve, flow through small opening, flow through orifice. These are the example of throttling process. So there is also some assumption is there. First assumption is that steady flow. For every component there is a steady flow is there. Steady flow. Second, that is why steady flow energy equation is applied. No heat transfer. No heat transfer. Transfer. Third assumption is that no work transfer. No work transfer. Fourth assumption is that change in kinetic energy and potential energy are neglected. Neglected. Now fifth assumption is that always occurs high pressure to low pressure. Always occurs high pressure to low pressure. Low pressure. Okay. Apply steady flow energy equation. Now apply steady flow energy equation. That is H1 plus C1 square by 2 plus GZ1 plus Q, that is equal to H2 plus C2 square by 2 plus GZ2 plus W. So here steady flow, that means this equation is applied. No heat transfer, this is cancel out. No work transfer, this is cancel out. Kinetic energy and potential energy are neglected, so this cancel out. So always occurs high pressure to low pressure. So from this equation you can see that H1 that is equals to H2. So for throttling process, the enthalpy, specific enthalpy of inlet, that is equal to specific enthalpy at outlet. Very, very important. So that is why throttling process is known as isenthalpic process. So hence throttling process are known as isenthalpic process. Isenthalpic process. Okay, thank you.